Hi everyone, welcome to the fifth lecture of this module 7 where we are discussing the force sensors. Basically this is a microsensors and nanosensors course, and in the previous class we have discussed the piezomagnetic force sensors and electroactive force sensors. In today's class, we will be talking about optical force sensors and little bit on vision based force sensors. Optical based force sensors and vision based force sensors are categorized under non-contact force sensors, and this is very beneficial when you don't want to actually touch the, or you even cannot touch the object on which you want to measure the force, or if you want to measure the deformation. Okay. So, let us discuss first optical micro force sensor, and then we will talk about vision based force sensors. Okay. So, those sensors which utilizes optical principles that include measurement of changes in light intensity, be its phase, or change in the polarization, or sometime change in the wavelength as well. Okay. So, if these things are changing when the force is applied, okay, you can actually measure the force if you are able to calibrate it against the sensors. Okay. So, usually a microstructure deflects means there is some displacement associated with it. Okay. Usually a microstructure either deflect or deform when there is a external applied force. Of course, in the case of microsensors or micro force sensors, this deflection are very small. Sometimes it even goes to nano dimension. Okay. So, a microstructure either have a displacement or deformation when there is a applied force, and this change is actually transduced into a measurable optical signal. This optical signal is in the form of, as I have just mentioned, in the form of either modulation of the intensity or modulation of the phase or polarization, or sometime modulation of the wavelength. All right. So, let us discuss some of the phenomenon which is helpful in developing optical micro force sensors, and the first phenomena that we are going to discuss is the intensity modulation, or the changes in the intensity that is detected by some photodetector or some other mean. Okay. So, force changes the amount of light that reaches the detector. Let us take one example. Okay. Say I have this object, okay, on which I am applying a force. Okay. Right. I am applying a force, or say this is object, here I am applying the force. Okay. Because of which there is some deformation in the object. Okay. There can be a displacement also if this object is moving to this place, for example. Okay. But let us consider the case of deformation. Okay. I have a, so this object is under applied force F. Okay. Now, say this is a monochromatic source of light, okay, and it is being detected here. Okay. We also have sometime reference sample, but let us talk about this sample first. Okay. I have a monochromatic source of light and a detector tuned to this emitter. Okay. When there was no deformation or there was no force applied, say the intensity that reaches this place is say I1. Okay. And say if there is a force F1 and there is some deformation, say delta or delta 1, the intensity is I2. When the applied force is F2, intensity goes to I3, because this deformation changes to delta 2 value, right, and so on. Okay. If you know the initial intensity I1 correctly, you will be able to find that what amount of force has been exerted on this, due to which there was a deformation delta 1. Okay. And because of that the intensity has changed to I2 value. Okay. The method is very simple, but also we have to sacrifice some point, like they are very susceptible to light source fluctuation. Okay. There can be interferences also if you don't choose the source of monochromatic light wisely. Okay. And because of these fluctuations of the source, because you cannot keep it constant for a longer time, there are drifts associated with it. Okay. Then there are other techniques like interferometric technique. Okay. Here force causes a phase shift in the light, okay, which leads to interference pattern changes, okay, or because of this phase changes. Okay. There are various kind of interferometers that exist in the domain, okay, and most of them can be used in case of micro force sensor application. Okay. We will also discuss them when we will talk about the displacement sensors, because in the displacement sensors also we will talk about change in the range of micrometer only. That is what we are seeing in the force sensors also. Okay. So, you have FP interferometer, Fabry-Perot interferometers, then you have Michelson interferometers, and Mach-Zehnder interferometer is very popular for this kind of application. Okay. The advantage of this kind of interferometric measurement is they have very high sensitivity, because they are dependent on the phase. So, little bit shift can have a larger phase changes. Okay. The resolution of these devices are also very high, as similar to the sensitivity. Okay. However, the setup is very complex. Okay. You have various mirror arrangement, various optical arrangements, which is very complex. Okay. So, it is not that easy to make these interferometers. Also, since they are very sensitive, they are susceptible to vibrations and the outer ambient condition changes like temperature changes. Okay. Then we have wavelength modulation based devices, or wavelength modulation technique, or sometimes we also call it spectral modulation. Okay. Here the force induces a shift in the resonant wavelength or spectral characteristic of a setup. Okay. For example, the setup can be a simple FBG setup, or which is called as fiber Bragg gratings. I think most of us has read about this, or we also have done practical in our first year of UG, where we do grating experiments. Okay. You can also have this spectral modulation devices based on resonant microcavities. Okay. The advantage of this kind of structure is they can be multiplexed. Okay. So, they have the ability for multiplexing. Okay. They do absolute measurement, so they can be classified under absolute sensor classes. Okay. However, the challenge here, challenge in this case of wavelength modulation based technique is the it require very precise spectral analysis. Okay. And you know that spectral analysis tools are very costly. So, this kind of instrument are not basically cost effective. Okay. Then we have polarization modulation based devices, where force alters the polarization state of the light. Okay. Most of these polarization modulation based devices are photoelastic materials. Okay. However, their resolution is not very high, and the sensitivity is also not that great. So, it is limited to maximum micronewton kind of forces. You cannot expect it to go to nanonewton or piconewton, which we have seen that for some devices is quite possible. Okay. Then one of the latest emerging optical micro force sensors are based on evanescent field sensing, where the interaction between light wave and the surrounding media is considered. Okay. So, these devices are very advanced devices, and they are based on measurement of evanescent field. Okay. So, however, these are different techniques, and based on them there are various class of devices that exist in the research domain at least. Okay. Practically, there are mainly 4 applied methods for detecting the microforce using optical technology. The first one is laser Raman spectrometer method. Okay. Then we have interferometers based on lasers. Okay. Then atomic force microscopy is perfect example of measuring force cleverly with light source, where light has little role, but then that is very, very crucial. Okay. Then we have optical tweezers based force sensor, or sometime you can extend it for pressure measurement also. These 4 techniques are very popular in force measurements. Okay. Let's discuss them very quickly before going to vision based force sensors. Okay. Let's talk about laser Raman spectrometer. We all have seen a laser Raman spectrometer, but how we can extend it for the measurement of force, let us see that. Okay. So, laser Raman spectroscopy uses a monochromatic laser source to interact with molecular vibration modes in a sample. Okay. We know that there are various laser sources which are very popular, like say 521 nanometer laser or 640 nanometer lasers. Okay. They are all monochromatic laser sources. They are very popular in Raman spectroscopy. Okay. So, what it does, it interact with the material. Okay. And then we have Stokes lines or anti-Stokes lines, depending on how it is interacting. Okay. So, the shifting of the laser energy goes downward if we have Stokes line, or it goes upward if you have anti-Stokes line. Okay. And they are based on inelastic scattering, right. So, laser Raman spectrometer method can be extended for the measurement of applied force by detecting the Stokes lines and anti-Stokes lines in this by Raman spectrometer. Okay. So, if you have this kind of configuration and if you try to deform your load, okay, what happen is there are changes associated with this Stokes lines and anti-Stokes line. So, initially there was some line associated with it, and when it is deformed, the spectra changes and it detects that, and based on that you can talk about the applied force, right. So, you can actually comment on the applied forces. Okay. The theoretical accuracy of this method is not very high, usually less than micronewton. Okay. The sensor is mainly used to realize non-contact measurement as any optical force sensor. Okay. The speed of detection is not very high because you have to have a complete setup of laser spectrometer or Raman spectrometer for this measurement. The real time capacity is poor for measuring multidimensional information, but nowadays with the advancement in Raman spectrometers, these things are not very difficult. Okay. So, the second technique in the row is laser interferometers. Okay. So, laser interferometers are based on change in path length, right. So, they can measure a very small force, may be extended to even below micronewton. Okay. So, these are used to calibrate displacement, small displacement like machine tables or slides, and axis movement that coordinate the measuring machines. Okay. Particularly if the ranges of this movement are in the range of micrometer. Okay. Depending on how they are excited, they can be of different type, like you can have a AC laser interferometer or DC laser interferometer, but the idea remains more or less similar, that it measures the change in path length with the existing laser source. Okay. So, this is a single beam AC laser interferometer arrangement, where you can see that how the area changes or the displacement changes is measured, right. Then another very popular force sensor is atomic force microscope, where actually it is not a microscope, but change in the or the interaction of a cantilever and a surface give you a idea that how the surface will look. Okay. So, it is basically a high resolution scanning probe microscope that maps the surface topography at a nanometer scale. Okay. So, it uses a sharp tip on a flexible cantilever, Usually this cantilever are made up of silicon, so you cannot expect it to be, when I say flexible, I don't actually mean like PET or other kind of substrate. I actually mean silicon only, but of course micro machined silicon, so they are flexible, not brittle. Okay, so it uses a sharp tip on a flexible cantilever to detect force between tip and the sample surface. Okay, the deflection of the cantilever is measured using a laser and a photodiode system. Let's understand this using a diagram. Okay, this is a silicon tip, okay, on which a laser diode is bombarded or laser light falls. Okay, now this laser light, the reflected laser light through this mirror arrangement falls on the photodetector. Okay, now when this tip goes below, okay, the position of the light that falls on this will change, right? Accordingly, the changes are reflected at the photodiode end. Okay, and based on this, we'll see how this tip will interact with the sample. Okay, there are certain amount of forces that when it comes very close to this sample, the force between tip and sample changes, and accordingly the laser position changes on the photodiode, and this changes are measured, or it can tell about the force between this tip and the sample. Okay, so depending on the sample type, AFM can operate in different modes. Mostly 3 different modes are popular: contact modes, non-contact modes, and tapping mode. Okay, so as the name suggests, contact modes means the tip is in the direct contact with the surface of the sample. Okay, non-contact mode is although the tip is very close to the sample surface, but it is not touching the sample. Okay, and then third is the tapping mode, means that the tip is coming very close or even sometimes touching the surface and going back. So it is basically tapping the tip on the surface of a sample. Okay, right. So depending on how close this tip is with the surface, okay, you can have different forces. Okay, so if say this is the distance, this x-axis suggests the tip to sample separation distance r, okay, and this is y-axis is force F. When it was very far, you have, when you close it, when you bring it near to the surface of the sample, okay, you have this attractive forces. So this tip is coming near to the surface. So this was at far, you are bringing it near and near. Okay, you have attractive forces, and this, in the non-contact mode, it works somewhere here. The AFM works in this force region. Okay, so basically what you can do is you can measure this force by seeing the interaction of this tip with the surface. Okay, now when it comes very close to the surface, at some point it will touch the surface. Okay, now it will be a repulsive force. Okay, so this is the intermittent contact area. Okay, and in the contact area, in the contact mode, it works somewhere in this range. Okay, so that is how AFM measures the force, and based on the measurement of force, it can predict that how the sample surface will look like. Okay, that's why, although if you see there are no optics involved, then also we are calling it microscope, because it can generate the or it can suggest the contour of the surface. Okay, then the fourth kind of optical force sensors are optical tweezers. Okay, these optical tweezers are also called as single beam gradient force traps. Okay, these optical tweezers uses a highly focused laser beam to hold and move microscopic and submicroscopic objects like atoms, nanoparticles and droplets in a manner very similar to tweezers. Okay, so it can manipulate at nanoscale. Okay, so using this optical tweezers, which is basically a very high intensity laser beam molded in such a way that it can act as a tweezer. It can manipulate or it can leviate basically a nanoparticle, or sometime even with the liquid media like nano droplets. Okay. The laser light provides both attractive and repulsive forces. Okay. These forces, depending on the relative refractive index between the particle and the surrounding medium, will change. Okay. This force is typically of the order of piconewton. Okay. So, they can measure very small forces like in the range of piconewton. Okay. So, the leviation is possible if the force of the light counters the force of gravity. When you are talking about leviation, even using a laser light, okay, what you are doing is you are pushing it against the force of gravitation, and that is the basis of its measurement also. If you remember, in the first class of this force sensor, we have discussed that we can measure the forces against various things, including balancing it against a gravitational force. Okay. The trapped particles, particularly the nanoparticles, are usually very small. Okay. And the leviation forces are, that's why, very small. Okay. So, if the light consists of photons that each having momentum p, the light of the specific wavelength lambda, the magnitude of the momentum of single photon can easily be given by h by lambda, where h is the Planck's constant, and based on this change in the momentum, you have radiation pressure, and associated with it will have the force. Okay. So, radiation pressure, if you see, is defined as the force per unit area on an object due to change in the momentum of light. Okay. So, you can also measure the radiation pressure with the help of optical tweezers. Okay. The application of this optical force sensors are enormous. Okay. For example, they can be used for measuring forces exerted by individual cells. Okay. That is why they are very popular in cell mechanics and mechanobiology. Okay. You can also use it for characterizing the surface properties and molecular interaction. We have already seen the AFM, which basically can help in characterizing the surface contours. Okay. It can also be used in sensors or biosensors, particularly by detecting biomolecular interaction based on force changes. Okay. They are very popular in microsurgery and other medical applications, particularly because you can, if you have a very precise microforce sensors, you can precisely manipulate the tissues. Okay. They are also very useful in names characterization as well as in the memes characterization by testing and validating the mechanical properties of micro and nano devices. Okay. You might have heard about nano indentation also. That is also possible because of micro force sensors. Okay. Then nano manipulation is something which is very crucial when you want to control the self assembly or other precision control at nano scale. Okay. In those cases also, this optical force sensors are very popular. In nanotechnology, they can be extended to measure elasticity, plasticity and fracture mechanics of thin films and nanomaterials. Okay. It can also help in characterizing interfaces, heterostructures as well as epitaxial layers. Okay. The advantage of optical force sensors are, the biggest advantage is they can be non-contact measurement. Please remember, let us recall first the first lecture where we discussed the strain gauge based sensors. Okay. Where what you have done is you have an object, you have literally glued strain gauge devices, okay, or a strain gauge, okay, to measure the deformation. Okay. Here you do not need any kind of this gluing external force sensing units. What you can do is simply you can do measurement using non-contact mode. Okay. Their sensitivity and resolution is generally higher as compared to these strain gauge based devices. Okay. They are very immune to the EMI. Okay. And they also have miniaturization potential. In fact, they can be very easily integrated with the MEMS technology. Okay. With this kind of devices, optical devices, remote sensing capability, remote sensing is possible. They have remote sensing capabilities. So, in the harsh conditions also they can be utilized. Okay. And all these optical force sensors have very high bandwidth. Okay. So, however, there are certain challenges and limitations, or you can say disadvantages associated with this optical force sensors. Like the first disadvantage you can say is the complexity of this optical setup. Okay. Talk about interferometers or any other kind of devices. Okay. Their setup is very complex. Okay. So, that is one of the disadvantage, but of course, it gives you very high sensitivity and resolution. So, you have to sacrifice on it. Okay. Then they are we have seen in the case of interferometers, they are susceptible to the change in the environment conditions. Okay. So, they are very much not that immune to the environment conditions, I would say. Okay. Then they will need calibration time to time. Okay, because of the optical sources as well as the lens system involved in it. Okay. So, you cannot expect a monochromatic source of light to emit only at 520 nanometer always. Okay. So, depending on various conditions, the emission wavelength can increase or decrease, or even it can become broadband if things are not monitored. Okay. So, the calibration is very important for these devices time to time. Okay. The dynamic range of these devices are very limited. Okay. Depending on the source of light that you are using, the dynamic range changes. Okay. However, the advantage I have already mentioned, that integration of these devices are not that difficult. It can be integrated with the current electronics. However, there are certain issues when you integrate this optical based force sensors. Right now, a lot of research is going in the area of silicon photonics. If that happens, if you have a source based on silicon, this integration is not that difficult also. Okay. Now, let us talk about vision based force sensors very quickly, so that we understand both non-contact force sensors. Okay. In case of vision based force sensor, the idea is to extract force information by observing the deformation of a known compliant structures or markers which you have put and it has changes under the applied force. Okay. And this is done using optical imaging. Okay. So, these are based on processing the image acquired at different times. Okay. So, these sensors uses some algorithms to calculate the force. What is the basis of the algorithm? We will see in a while. Okay. As compared with other sensing methods, this sensor can easily be implemented. Okay. Because a microscope is only necessary device in this micro manipulation. Okay. And it can measure the force very much reliably, particularly in the case of the marker based devices. Okay. The methodology for this measurement is very simple. Say you take a cantilever with known mechanical properties that deform predictably under the force. So, you know that when you applied this much force, how this cantilever is going to bend. Of course, this cantilever is just one example. It can be based on microplatelet, it can be based on diaphragm, depending on what structure you have. Okay. Then high resolution microscope is required. So, high resolution microscope or camera is required to capture images of the compliant structure, or sometime you can attach markers. So, you have to see the positions of the markers when you have already applied the force. Okay. Now, what you have to do is, the last step is use image processing algorithms. Okay. This image processing algorithm is mostly based on various techniques, but the crude idea behind all this algorithm is the feature detection first. Okay. So, you identify important markers. Okay. Say for example, if say this is an object. Okay. This is an object, and say in this object, if I have a small cut over here. Okay. So, the structure of this object is something like this. So, this is a say micro cut in this, say the depth of this cut is around say 0.5 micron. Okay. Now, when you deform, okay, by capturing this optical image of this this cut, or even if there is some crack, for example, by observing this can be one of the marker, right. So by observing the change in this crack or in this cut, okay, you can find the applied force, okay, you can at least predict the applied force. So this is very important, that when you try this vision based force sensor, you first identify the feature that you want to use in this image processing algorithm, okay. So first is the feature detection. So the idea is to identify important markers, edges or pattern in the structure, okay. The second point is tracking, okay. So you quantify the deformation of these features by quantifying them, and it is possible by tracking them, okay. So by sequence of images you can track them, okay. And the final one is the force calculation, okay. Once you have this, you can have force calculations. So for example, by applying calibration curves or mechanical models to convert deformation into force. Sometimes it can be in the form of displacement, for example, okay. Say if there is some force applied and there is a displacement. So the simple model can be, say if it is a spring based device, it can be k into delta x kind of equation can simply be used, of course with a lot of assumptions, and by considering different boundary conditions you can utilize these equations, okay. So the techniques can be marker tracking, as we have just discussed. I mean, these are all internal markers that I have talked about. There can be some external markers also that can be put by attaching micro beads or patterns and tracks. You can have all these things, and by tracking their movements you can actually track your marker, okay, and based on sequence of figures you can implement your algorithm, okay. Then shape and boundary tracking can be another way. So analyze the deformation of the entire compliant structure of course at micro scale, okay. Then interferometry or optical lever based analysis also exist, where using light interference patterns to detect tiny deflection, particularly when the microstructure are in the range where this interference patterns can be generated, okay. So this is very crucial when you are talking about very small forces, okay. So in those cases this interferometer based vision force sensors can be applied, okay. The detecting accuracy of this vision based force sensors are in the range of millinewton or sometime in the range of some millinewton, but this can be extended with the advanced microscopy techniques that exist and smart algorithms that exist, and if you can integrate it with the AI and machine learning models, okay, the prediction even become more and more accurate, okay. It can achieve a nano-Newton resolution in measuring static forces, but of course as I have mentioned that it can also be transformed into dynamic forces, okay. The force distribution in a linear elastic object can be determined using a contour information extracting from the image, okay. This can be a suitable example for a vision based force sensor, okay. The force distribution in a linearly elastic object can be determined using the contour information, which is of course deformed under the applied force, okay. The energy minimization method can be used to match the deformed template of an elastic object to the contour data in an image, okay. So this can enable the algorithm to be suitable for real time applications. So there are lot of algorithms that has been reported in recent time for this vision based force sensors, okay. The advantage of this vision based force sensors are they can map force distribution over a small area, okay. So usually what we do is we employ our say optical force sensor or a say strain gauge based force sensor in one area, okay. But in this case what you do is, if you have say this kind of object and force is being exerted in all the area, and the deformation you don't know that is coming from all this area, okay. This small area, the distribution of the force in this small area can be calculated by this vision based force sensor, because it can take the complete contour in one go, okay, because this is image based analysis, okay. As I have mentioned, they are non-contact based measurement methods. Okay, so measurement which prevents interference with the delicate samples like biological tissues or say soft materials. Okay, in those cases this vision based force sensors are very useful, very similar to the optical based force sensors. Okay, they are capable of measuring forces in the range of nanonewton to piconewton when you are talking about static forces. Okay, they are applicable to a wide range of materials and biological systems, particularly the soft systems. Okay, they allow for the direct visualization of the interaction while measuring the forces. Okay, however, there are certain limitations associated with this vision based force sensor, like it require precise calibration of the compliant structure's stiffness and accurate image processing. Okay, these devices are susceptible to temperature fluctuations, vibrations, and refractive index changes. Okay, so from the image you will predict that this force has been applied in this area, but the cause of that force might be, cause of the deformation can be something else. Okay, so the real time force measurement can be computationally intensive, especially for high frame rates and complex algorithms. Okay, so usually when the force is applied, after that you monitor it. So real time monitoring is quite complex in this case. Okay, then precise alignment of the optical system is critical for accurate measurement. Okay, when I say optical system here, I am talking about a microscope. Okay, so if I have say this object under investigation under a microscope, okay, and I have say this lens system. Okay, now if either my object is in different, the orientation of the object is different, or the lens orientation is different, or if it is not focused properly. Okay, it can give some, if the captured image itself is out of focus. Okay, the prediction can go all wrong. Okay, so the alignment of the optical device that you are using, be it a camera or be it a microscope, okay, you have to be very crucial while aligning them, because it plays a very critical role for this vision based force sensor. Okay, a single sensor might have a limited range of force it can accurately measure. Okay, then integrating vision systems with micro manipulators is very complex. Okay, so you have to monitor the images from all the area in real time, and then at the same time you want to implement the algorithm at the same time. Both are very difficult. Okay, so with this we have finished our this module of force sensor. We have seen both contact based force sensors as well as non-contact based micro force sensor. We have seen that some devices has capability to measure sub micro Newton forces, and some devices can be extended for the measurement of force in the range of nanonewton to piconewton. Okay, so with this we have finished this module on force sensors. We will discuss other things in our next module. Thank you.